Hello, this slideshow is on ideal gases and the ideal gas law. And the essential question today is, what is the difference between an ideal and a real gas, and what is the ideal gas law? So there are many situations in this class where we will learn things first from an ideal perspective. An ideal is sort of the simplest practical model of something. And we do that because obviously once you understand the basics of it, then you can add nuances of the real world. Considering objects and systems to be ideal from the start allows us to make kind of back of the envelope calculations or really quick predictions about their behavior, assuming that the gases act in a predictable way. So you need to be a little bit clear on what are the assumptions we're making about this system so that our basic set of equations work. Because in the real world, some of the equations get a little bit messier. So here's an example of sort of an ideal ice cream cone, and in a minute, we'll see how the real one is a little bit different. Real objects or systems are often behave similarly to the ideal object, but there might be a few like nuances or differences based on reality, things that we've been ignoring or pretending didn't exist. So there's my real ice cream cone, obviously similar to the original, but there are some nuances about that real one that are a little bit different. So in this unit, we're going to start by trying to understand how ideal gases act. And ideal gases come with a series of assumptions. So the first assumption that we're going to make when we use the word ideal is that we're going to assume that our gas particles are very tiny and there is a lot of space in between those gas molecules. And that's pretty realistic in most conditions in the world, right? If you look around you at the air, the particles are tiny and there's a whole lot of space in between. The second assumption is that all collisions between anything happening are going to be perfectly elastic. So what that means is the gas molecules are moving around, right? We know that they have motion. Eventually they're going to bump into things. They're going to bump into each other. They're going to bump into the walls of the container. But when they do, they're going to bounce off perfectly, okay? And that means no energy is going to be wasted. We're not going to turn any energy into heat via friction. We're not going to have any squishing of the gas molecules because that heats them up as well when they kind of squish against themselves. We're going to assume these are like these perfectly bouncy, hard spheres that hit and bounce straight off without wasting any energy. The third assumption is that there's no intermolecular forces between the particles. That means the only time those little gas molecules experience a force is when they hit each other or hit the container walls. They are not going to be pulled together via gravity. They're not going to be electrically attracted or magnetically attracted or repelled from each other. So they're just moving in space until they bounce off of something, and no other forces are going to be acting on them along the way. And then the last assumption is that they're going to follow this equation known as the ideal gas law that we're going to be learning about in the next handful of slides. So realize that these are all assumptions, and in the real world, real gases, to some varying degrees, violate these assumptions, right, under various conditions. And so while we're going to start by understanding how ideal gases act, if a problem or question asks you, how would a real gas act, and they're going to tell you more about the real gas, you'll need to be aware of of what assumptions we made and how changing the reality might impact the system that we're talking about. So the ideal gas law is an equation. It's an incredibly useful equation. We're going to be using it a lot. Sometimes you hear this equation called PIVNERT. You may have learned it in chemistry, but it is the equation that relates all of the main relevant variables for an ideal gas. So the variables that have relationships represented in this equation are pressure, which we've worked with a lot. Okay, pressure is capital P and the units are pascals. Volume, which we're also very familiar with, capital V, and the units are going to be in meters cubed. The third relevant variable is the number of moles of the gas. So how much gas are we talking about in our system? We use the letter lowercase n to represent that, and the units are going to be the mole. And then the fourth variable is temperature, which is a capital T, and the units for that are Kelvin. So we already know all those variables. The question is, how do they relate to each other? When we're coming up with this series of equations, I usually think of pressure as my dependent variable because if I give you a gas system and I say, set it to this pressure, like probably you can't do that. There's no way of like mechanically setting the pressure of a system. It is much easier to mechanically set the volume, right, by putting the gas in a specifically sized container. You can measure how much gas, how many moles of the gas you put in and out, or prevent that from changing. And then temperature is generally a pretty easy one to change as well, because you heat it up or cool it down, you can change the temperature. So usually those other variables are our independent variables that we are controlling via our experimental setup, and the pressure is kind of the thing that we're measuring the effect of those other variables. So given that, how would we experimentally determine the relationship between pressure of a gas system and the volume of the gas system? The first thing you need to be able to do is to have a container that's volume can change, okay? Because if we want to have a relationship, we have to be able to change one variable and measure the effect on the other. So what kind of container could you change the volume of? It's got to be flexible somehow, an accordion kind of container. The common situation involves something known as a piston, which I'll show you a picture of in just a minute, but it's sort of a container with one side that can squish in and out. So that's a good way for physicists to be able to physically manually control the volume of the container. The other aspect of this experiment is that we're going to have to hold the other variables constant. So if we want to see just the effect of changing pressure or changing volume on the pressure, we're going to have to hold everything else constant. So if we want to hold N constant, that means my container has to be closed. It can't have any leaks. And holding temperature constant is a little bit tricky. Typically what physicists do is they use something called a hot or a cold water bath. So you're going to take your whole container and you're going to put it in water that has a specific temperature. And the reason that works really well is because water actually can store a lot of heat. Water, it's hard to change the temperature of water. It's another one of the remarkable properties of water. So putting something in water, those things are going to assume the same temperature of the water, and they're going to keep that temperature really reliably. It's a nice way to kind of insulate it and keep the temperature in. So we're talking about a container where we change the volume, okay? We hold everything else constant, and we're going to have a pressure gauge in that container that allows us to measure the pressure over time. So here's an example of that container, and that's that piston that you see up at the top. If you pull up on the piston, you are going to be increasing the volume. And if you push down on the piston, you're going to be decreasing the volume. And if you hold everything else constant, what you find is that increasing the volume is going to decrease the pressure, and decreasing the volume is going to increase the pressure. From a kinetic theory explanation, the bigger the volume in the container, the smaller the volume in the container, the less distance there is between the container walls, and that means that we're going to have more collisions every second, and that's why the force and the pressure is going to go up. So you should both be able to say there's an inverse relationship between P and V, right? So the bigger the volume, the smaller the pressure, and vice versa. And you should be able to explain why does this make sense from a molecular level or from a kinetic theory level. And the reason is because, you know, the spacing has changed, and therefore the number of collisions every second is going to be going up. So the second relationship that is going to go into making our ideal gas law is the relationship between pressure, again, as the dependent variable, and N, which is the number of molecules. So if we're wanting to change N, we have to have some sort of port in our sample that we can add gas through. Then we want to keep the volume constant, which means we have to have a fixed container, or sometimes called a rigid container. So this is one without a piston. We're not going to allow the container size to change. And we're going to also hold temperature constant, again, with a hot water bath of some kind. Then we're going to be, again, measuring pressure with some sort of pressure gauge that we have attached to our container. So this would be this kind of situation, right? I'm keeping the volume the same, but I am putting more gas in through that port, and then I'm measuring what happens to the pressure. Probably won't surprise you to realize that there is a linear relationship between N and P. So obviously, the more gas molecules in my system, the more pressure we have, because they're going to be colliding with the container walls more often every second. So you should be able to say, mathematically, it's a linear relationship between N and P. And conceptually, from kinetic theory, the reason is because there's more collisions with the wall every second, causing an increase in pressure. The last relationship that's going to go into our ideal gas law is the relationship between pressure and temperature. So again, we got to think about how are we going to change our independent variable. In this case, you can change the temperature of your sample through the application of heat or ice. So you're going to heat it up or cool it down with fire or some other way, or cool it down with ice. And then we have to hold the other two variables constant. So we've got to have our rigid container to keep the volume constant, and we are going to have it closed, so no leaks, which is going to keep the N constant. And again, we're going to be using a pressure gauge to measure the pressure. So that looks something like this, right? I've got my container with a fixed piston position and no leaks, and I'm going to go ahead and throw some heat at that container and see what happens. Hopefully it would make sense to you that as we add that heat, we're going to increase the pressure of the container, showing that there is a linear mathematical relationship between temperature and pressure. The kinetic theory reasoning is because the hotter the particles, the faster they're moving, and that means each collision with the container walls is going to exert more force on the container walls and increase the amount of pressure that they are experiencing. So the ideal gas law is an equation that combines all of the contributions of those individual relationships into a single overall equation. As we know from the previous 3 slides, pressure is linearly related with the number of molecules in the container and the temperature of those molecules. So we're going to be putting them on the top of the fraction. And it is inversely related with the volume of the container, so that's going to go on the bottom of the fraction. Turns out, though, if you multiply together the units of those relationships, so the moles times Kelvin divided by meters cubed, you don't get pascals. So we need to have this constant that we throw in there. It's just a proportionality constant. It's just a number, but it has funky units that allow the units to come out. And we determined the value of that number sort of experimentally, putting in 1 mole of gas at 1 degree Kelvin divided by in a volume of 1 meter cubed, and we measure what the pressure is, and then we're going to put this little fudge factor constant in there to make it come out correctly. So that constant is known as the universal gas constant, and it's written in an equation with the letter R, but it's just this number. It's 8.31. Units are joules per mole Kelvin, and that's how we get our units and our values to come out with things that we're familiar with. So once we put that in there, we're going to rearrange this equation slightly, which I don't love, but they do it on the equation sheet. And so what they did is they multiplied the V out and they included that R. And so now my equation, which shows all the same relationships, is PV equals nRT. And that is sometimes known as PIVNERT because it kind of looks like the word PIVNERT. So there you go. We've derived the ideal gas law, and this equation can be used to calculate values, and it also is the equation that shows all the relationships that we sort of figured out experimentally in the previous 3 slides. Okay, we've reached the end of the slideshow, so take a minute and revisit your essential question, which is what is the difference between ideal gas and a real gas, and what is the ideal gas law? How could you use it to make calculations quickly about a system of gas? Enjoy the comic. Thanks for watching.